All right, I am sure you're excited to see applications of that change of variables formula that we ended the last video with. And so we're going to do a couple of examples right now. Let's evaluate the double integral of x plus y dA, where r is the parallelogram whose vertices are 0, 0, 5, 0, 5 halves, 5 halves, and 5 halves, negative 5 halves. And I'm giving you the transformation. So we're going to use x equals 2u plus 3v and y equals 2u minus 3v. So first thing we want to do is sketch the region and determine the equations of the boundary lines. And I've already done that, and I've already found the equations of the lines. So the next thing we're going to do is use the transformation on each of these lines to determine the region we have in the UV plane. All right, so let's do y equals x. We do y equals x, we have 2u minus 3v is going to equal 2u plus 3v by substituting. Algebra gives us that 6v is equal to 0 or v is equal to 0. For y equals negative x, we have 2u minus 3v, that was our transformation in y, is equal to negative x, which is, so we have the negative of the quantity 2u plus 3v. So we have 2u minus 3v is equal to negative 2u minus 3v, add 2u and plus 3v to both sides, we get 4u is equal to 0, so u is equal to 0. And the line y equals negative x plus 5, we're going to have 2u minus 3v is equal to negative of the quantity 2u plus 3v plus 5. Again, doing our algebra, we're going to see that 4u is equal to 5, so u is equal to 5/4. Finally, we have y is equal to x minus 5, so we have 2u minus 3v is equal to 2u plus 3v plus 5. Phew. Add 3v to both sides, add 2u to both sides. That's not right. Subtract 2u from both sides, subtract 3v from both sides. I get negative 3v is equal to negative 5, or v is equal to 5. That's a 6, isn't it? 3 plus 3 is 6. 6v is equal to negative 5, so v is a positive 5/6. Awesome. So that tells us that the region S is the rectangle with sides u equals 0, v equals 0, u equals 5/4, v equals 5/6. And then the ranges of u and v are going to be, well, u is going to be between 0 and 5/4, and v is going to be between 0 and 5/6. Excellent. Now the Jacobian is, right, j of uv. That's the determinant of x sub u, y sub u, x sub v, y sub v. So we have the determinant of that matrix. So that was 2 from 2u minus 3v and 2 from 2u plus 3v. That's reversed, right? The way x was 2u plus 3v, y was 2u minus 3v. And so x of v is going to be, since that was a plus 3v, was 3, and the y sub v is minus 3. So I'm going to get 2 times negative 3 minus 2 times 3, which is, I believe, known as negative 12. So finally, we get our integral, and our integral is going to be, check this out, our integral is transformed to the integral from 0 to 5/6, integral from 0 to 5/4 of 2u plus 3v plus 2u minus 3v du dv, oops, By the way, don't forget to put the absolute value of the Jacobian. du dv. So that's just a regular absolute value. Simplifying, we obtain the integral of 48u du dv, right? Because the absolute value of negative 12 is 12. Okay, so I'm going to get the integral from 0 to 5/6 of 24u squared evaluated at its limits. So 0 to 5/6 of 75 halves dv, which gives me 75 halves v evaluated at its limits, which is going to give you, when you plug in everything, 125/4. So that's one example. And of course, I gave you the transformation. Now, the most difficult part of these problems is determining the transformation. So here we go. Let's evaluate the x squared minus xy plus y squared dA, where r, the region we're integrating over, is x squared minus xy plus y squared less than or equal to 2, using an appropriate transformation to simplify the problem. So we have to figure out the transformation. So we obviously want to change the region to a simpler one. This looks like an ellipse or something. Who cares if it's actually, I lied, it's not an ellipse, but it's not fun. I don't even want to try to figure out exactly what that is, but our goal, let's say, is to transform this rather unpleasant region into a disk centered at 0, 0. Okay, so we likely will need a transformation of the form x equals a times u plus b times v, and y equals a times u minus b times v. And why might this work, you might ask? Because, you know, it's not like we. And the reason is because if you do this, x times y is going to be a squared times u squared minus b squared times v squared. And so we replace the xy term by a difference of squares. So that's liable to make our life more pleasant. All right. So let's substitute x equals au plus b times v and y equals a times u minus b times v into the equation, well, into the left-hand side of the equation. So if I do that, x squared minus xy plus y squared is going to become a times u plus b times v squared minus, well, I already figured this one out, a squared u squared minus b squared v squared plus a times u minus b times v quantity squared, which gives us a squared u squared plus 2abuv plus b squared v squared minus a squared u squared plus b squared v squared plus a squared u squared minus 2abuv plus b squared v squared. And that's going to reduce to a squared u squared plus 3b squared v squared. So life will be good if we can find in two numbers, a and b, so that a squared is going to be equal to 3b squared. And we also want, because we have this 2 on the right-hand side, we'd like both sides, in fact, we need both sides be divisible by 2. All right, so what does that mean? that means that we need to choose A and B so that A is equal to the square root of 3 times B, and that they're both divisible by 2. So one possibility, and I'm just going to say, for example, we could choose 3b squared is equal to 2. That's divisible by 2. And so then B is going to be the square root of 2 over 3, and A is going to just be the square root of 2. Because it's square root of 3 times B, which is square root of 2. So therefore, a transformation is x equals square root of 2 times u plus square root of 2 over 3 times v, y equals square root of 2 times u minus square root of 2 over 3 times v. And this gives the region S of, well, 2u squared plus 2v squared is less than or equal to 2, or u squared plus v squared is less than or equal to 1. Yay, the unit disk. Okay, well, we already computed the integrand, right? Because the integrand was x squared minus xy plus y squared. Now we just need the Jacobian. So we'll compute the Jacobian. J of uv, remember, is the determinant, x sub u, y sub u in the first row, x sub b, y sub b in the second row. So we have a root 2 and a root 2 and a root 2 over 3 and a negative root 2 over 3. So that gives us root 2 times negative root 2 over 3 minus root 2 over 3 times root 2, which is negative 4 over root 3. Finally, our integral is the much simpler 2 times u squared plus v squared, absolute value of negative 4 over root 3, du dv, and then convert to polar coordinates to compute it. So I will do a short form of that. So we're going to get the integral from 0 to 2 pi, integral from 0 to 1, 2r times 4 over root 3 times r dr d theta. I meant to say 2r squared. So the constant's 8 over root 3, so we could pull that out. The integral from 0 to 2 pi, integral from 0 to 1 of r cubed dr d theta. So we're going to have 8 over root 3, integral from 0 to 2 pi, r to the 4th over 4, 0 to 1 d theta, which gives us 8 over root 3, integral from 0 to 2 pi of 1/4 d theta. So I'm going to end up with 2 over root 3 theta evaluated at the limits. Finally, I get 4 pi over the square root of 3. Phew! So as you can see, these problems take a while. It was not super easy, right? Because what took us the longest was finding the transformation. But once we found the transformation, we can go use the tools that we already have. Now, you might think triple integrals are going to be like way freaky harder, and it's really not so bad, relatively speaking. Works the same way double integrals do. Pardon my lack of ability to write grammatically correct, same way as double integrals do. But the Jacobian this time is defined by the derivative, where each row is just the derivatives of all 3 components with respect to u, v, and w. Special examples actually are the conversion formulas for cylindrical and spherical coordinates, right? You can derive those using this exact approach that we've done. Some suggested exercises for you. And next time we're going to be working on something called vector calculus. So that's sort of a bit of a change, but things are going to relate to what we've done. Have a great, great day, everybody.